All right, hello, we're going to do some work on related rates. Now, one of the things about related rates, so rate, that's kind of a calculus thing, right? The rate of change of some function. Velocity is the rate of change of distance. Acceleration is the rate of change of velocity. So related rates is part of calculus, but it's almost more algebra because basically what you have, you're going to be given one rate and you have to algebraically relate it to the rate of change of the other thing. So basically what you're doing is you're looking at a situation and then you're going to figure out how two variables are mathematically related, area and the radius, whatever like that. And you're going to already have the rate of change of one, and we're going to use that algebraically almost, really, I mean, there is a one differential in there, but a derivative, but to figure out the rate of change of the other one. So let me start with some basic rules for doing this, and then we're going to do a lamppost problem, and then later on I will post solutions to the problems on the worksheet that I posted too. So here's the basic way to solve related rates problems. So you're going to have a situation where you're going to be able to relate, figure things out in a static kind of way. That would be the geometry kind of way, or the trig kind of way, right? You're going to be able to figure out statically, but you're going to have something that changes, and you have to then take the derivative so that you can insert you'll be given a rate of change of one variable, and basically all you're doing is setting up the relationship between those. And once you know the rate of change of one variable, then you use that to establish the rate of change of the other variable. All right? Okay, so here's what we do basically. Start out by drawing a picture. Draw a picture of the situation because it's just a good way to get started. It kind of orients you, gets your hand moving, and anytime you just get moving, you just feel a little bit better, right? So just start by drawing a picture of the situation that you're trying to model mathematically. So then you got to figure out an equation that relates the two quantities of interest. So you have to figure out, if you know the radius, what's the area? Or if you know the radius of the sphere, what's the volume? Or if you know the radius of the cone and the height of the cone, what's the volume? Or if you know the lengths of one triangle that's similar to another triangle, that kind of thing. All those different things. You can. I have it on the screen there. You're probably going to use some sort of geometric fact, or a trig function, or the Pythagorean theorem, or similar triangles. There's going to be some way that you're going to be given one rate of change, and that was the rate of change of one variable. That is the derivative of whatever that variable is doing, right? It's the rate of change. So you're going to be able to develop a static equation that relates that variable that you know the rate of change to the other quantity. And once you do that, then you can do the mathematical magic that will get you the related rate of change of the other quantity. So let me get my document camera back on there, and we're going to do this situation here. We have a 6-foot tall dude walking 8 feet per second away from a 22-foot tall lamppost. Okay, so we're gonna start out by sketching it. We've got a lamppost, and the lamppost is shining, and that's a 22-foot tall lamppost. And then we have a dude. Could be an alien, could be anything, could be a chick. And this person is 6 feet tall. And this person is the situation we're trying to figure out. So we're gonna have that's our light shining, right? So our shadow is gonna be this distance. Now, if you have a constant, it's okay to put the actual number in. I know when I did this before I put h there, but you can just put the number in. If you know it's a constant, you can just pick the constant. Why make it harder? And then so we got the length of the shadow, and then we have the distance that the guy is traveling, and that's x. And the distance the guy is traveling, the distance from the lamppost, is the distance we already know the rate of change of which we know the rate of change, right? Because we know that the guy is walking at 8 feet per second. 8 feet per second. And that's a rate of change, right? And so the x is changing at 8 feet per second. So now we know dx dt. That's the rate into change of x with respect to time. Because that's another way to look at these problems, is an implicit differentiation of two quantities with respect to time. So we have the length of the shadow, and then we're also going to have to find out how far the tip of the shadow is moving. That's the easy part. So we'll call this length L. All right. So do we have everything? So the problem asks, so what's going on when he's 19 feet away? So the setup of this is he is 19 feet away. So our x is going to equal 19. But when you set up the problem, even though the x is 19 here, you don't want to put 19 in yet, because we need to be able to differentiate that, right? We need to get dx dt, not just x. All right, so now what we're going to do is set this thing up. And it's similar triangles, so you can set it up any way they're related. Pick the easiest way. I mean, if you scan the internet, you'll find this problem done with trig and all sorts of stuff. But and you might have to do trig, right? You might have to find the rate of change of this angle as the guy walks away or something like that. But right now we're just going, we want to go 1 is how fast is the shadow growing? How fast is the shadow growing? So just the S. And then 2 is going to be how fast is the tip of the shadow moving along the sidewalk? How fast is the tip of the shadow moving? And these are both at x equals 19. So that's the snapshot we're going to take. All right. So these are similar triangles, 6 and s, and 22 and x plus s. That's one way you could relate it, right? And that's what we're going to do for this one. And you could choose other ways, and you will find, if you do a few of these, you'll start to see ways that work well for you. So we're going to relate, we could do this over this, and then this one over this one, and then this one over this one, right? Those would also be legitimate relationships for similar triangles. But we are going to do this over this. Yeah. No, we're going to do this length over this length equals this length over this length. Again, you get, and I actually ran it both ways just to make sure I knew what I was doing before I showed you. You could pick whichever one you want, because math's math. And when math is doing what it's supposed to do, that's what it does. So this one is supposed to be, I'm trying to talk and write at the same time. So there we go. So we have this length over that length equals that length over that length, right? Okay. So the first thing we want to do is get rid of the fractions. So we're going to put the 22 over there. And so we're going to have 22s equals 6x plus s. That makes sense? Good. It should. That's pretty straightforward. Next thing we're going to do is we're going to distribute that 6. And we're going to try and keep things really neat, because I'm trying to show you how to do it, which is what you need to do, because you're trying to show your teacher or the AP grader or whoever that you know how to do it, right? Okay. So now we're going to take this and subtract it from both sides. And then we're going to get 18s. I feel like I just did something wrong. No, that's fine. Equals 6x. All right. And now, (22 minus 6 is 16, isn't it? I knew there was something going on. I have some notes off to the side, but they're actually different. So anyway, here we go. All right, so now what we're trying to do is get s by itself. We want to get s by itself, and then we're going to do the derivative, right? So now we're going to have s equals 6 over 16x. And if you want to reduce that fraction, you certainly can. S equals 3 over 8x. Okay, so now what are we looking for? We're looking for how fast is this growing. So what we're actually looking for is the rate at which s is changing over time, right? So basically what we're going to do is do the derivative of s and the derivative of x with respect to time. So then we're going to say ds dt equals, and that's a constant, so we can keep that outside of things. And look, we know just about everything there, right? So ds dt equals 3/8, and we are given dx dt, right? Because that's just how fast the guy's walking, the rate of change of distance from the lamppost. So that's 8. Wow, did that work out nice? The 8's cancel out, so the rate at which that shadow is moving, the rate at which the rate at which the shadow is growing, that's our s. That's just 3 feet per second. Now, we know that the L equals x plus s. So that's the answer to 1, right? That's how fast the shadow is growing. And now we want to know how fast the tip of the shadow is moving. So that's just our length L. And so now we're going to do the derivative of that because we want to know how fast that length is changing, right? So that's going to be dl dt is going to equal the rate of change the guy's walking, right? Plus however fast that shadow is lengthening. And lo and behold, we actually already know both of those now. So that is going to just equal dx dt, which was given in the problem, 8 plus the length of the shadow, how fast the rate of change of the length of the shadow is 3. So that equals 11 feet per second. And we're done with that. All right, so that's a simple walkthrough. Just to go back over it again, you're going to have two quantities that you can relate in a static way, and you got to figure out how to boil it down to two variables, one of which you're already given the rate of change for. So whether it's a sphere or it's a puddle growing or it's the volume of water growing or diminishing in a cylinder, a tank, or whatever, it's going to be quantities that you can figure out how to boil the thing down to two variables. And one of those variables you already have the rate of change of. And then you can use the equation that you figured out that relates those two variables. And then you insert the rate of change. And then you figured out the related rate of change. Does that sound good? Hope so. Bye.